going to talk about the central limit theorem, and we're going to talk about sampling distributions today. So it's a little different. It's kind of a extension of lesson 6.3. Suppose a team of biologists has been studying a Pinedale Children's Fishing Pond. It's supposed to be X represent the length of a single trout random from the pond. The group of biologists determined that the normal distribution with a mean of 10.2 and a standard deviation of 1.4. Okay, so this is what we did 6.3. What's the probability that a single trout, one trout taken at a time, would be between 8 and 12 inches? So of a single trout that's taken from the pond is between 8 and 12 inches long. So we know the mean, so it's a normal. The mean is 10.2 and the standard deviation is 1.4. So I'm going to draw this out on a normal curve. I'll draw a white trash normal curve. In the middle, I'll put the mean, 10.2. And then I'm concerned between 8 and 12. Now, do you have to do this, as I said a lot the other day, do you have to draw up this curve? No, you could do it. You could visualize it in your head. I'm just doing this for teaching purposes. We're wanting to know the probability that it's between 8 and 12. The probability of a single trout, if I selected at time, would be between 8 and 12. So I could use the z-score, but I'm not going to do the z-score here. I'm going to do normal CDF using the calculator. So second vars, normal CDF. My lower bound, where does the shading start? How far left does it go? 8. How far right does it go? 12. My mean is 10.2, and my standard deviation is 1.4. Okay, so pretty straightforward here. Okay, and so we get 0.8427. Okay, so that is the probability of a single trout. Okay, so you could also do the whole, find a z-score. You don't have to write this down. Don't worry about writing this down, but you could do a z-score where you'd have to do a z-score for each one. 8 minus the mean divided by the standard deviation, z equals, as I said, you don't have to worry about knowing this. So you could do z-scores for each and then find their areas. Okay, but 0.2 divided by 1.4. This way is just not very efficient, though. About 1.4. So negative 1.57 to 1.28. And then you would find the probabilities using the z-table. So negative 1.57. 0.5058. This is how we had to do it back in the day. 0.582, and then you find the 1.28. Okay, 1.28. 0.8997. So as I said, this is kind of and salt makes it even easier. So 0.8415. A little off because of rounding, but anyways. So that's for a single trout. Okay, 8415. Now, what you're going to learn today is we're going to learn something called a sampling distribution, where we're going to take a sample of more than just a single trout. We're going to do multiple at a time. Okay, and so what's the probability that the mean length of 5 trout? So we're doing 5 at a time. On this one, we had 1 at a time, a single trout. This one, we have 5 at a time. So when we're doing 5 at a time, we call this a sampling distribution. Our mean of the sampling distribution, mu of x, is equal to the same thing as the mean there. So the mean's going to be the same. But we do more than 1 at a time, what has to happen is our standard deviation of our sampling distribution changes. So what do I do with that? I divide it by the square root of n. So basically from here to here, the only thing that changes is you divide the standard deviation by the square root of n. So 1.4 divided by the square root of 5. Okay, so that's 0.626. And now you're going to do this you're going to do the same thing with these parameters. Okay, so when you're doing more than 1 at a time, the spread becomes less, because if I'm taking 5 trout, like the main length of 5 trout, some might be bigger, some might be smaller, and their average is going to be closer to what's expected, what's in the middle. So I'll do normal CDF. I'll probably confuse you with the Z stuff. 8, 12, 10.2, 0.626. CDF 8, 12. So the only thing that changes, so if you run it, just to simplify it, the only thing that's changing here is a standard deviation. So if I do one at a time, it's basically divided by the square root of 1. It doesn't change the standard deviation. If I do more than one at a time, I divide by the square root of n. So this would be 0.9978. And so a lot higher probability because the average of 5 is going to be a lot closer to the mean than one single one. Okay. Why are the probabilities different in examples A and B? Well, here's the thing. What changed from A to B? The standard deviation. Okay, so this because the standard deviation is smaller in B, what that means is you will have a higher probability around the mean. A higher probability around the mean.